The cordless drill driver, the ubiquitous implement for both fastening and drilling. The internal mechanics do not rely on raw speed. They depend on electromagnetic regulation. The brushless DC motor takes DC voltage from the 18-volt battery pack, generating a rotating magnetic field via internal coils. This drives an essential multi-stage planetary gear reduction system, chemically multiplying the motor's initial rotation into immense controllable kinetic torque at the chuck. The impact driver. While visually similar to the drill, its function is entirely disparate. This device is engineered for maximum fastening force via micropercussion. Inside, the high-speed brushless motor drives a robust hammer and anvil mechanism. It does not apply continuous torque. Rather, it rapidly converts rotational energy into brief, violent kinetic impacts thousands of times per minute, driving fasteners through material density that would stall a conventional drill. The SDS rotary hammer, built for brute force penetration into masonry and concrete. Normal drilling cannot penetrate aggregate, it overheats. This heavy-duty tool combines rotation with a sophisticated electropneumatic beating action. A motor-driven piston compresses air, which then drives a robust internal striker directly into the SDS chuck, delivering focused, high-joule impacts that pulverize the concrete substrate while simultaneously clearing the resulting pulverized aggregate. The sliding compound miter saw, a precision instrument defining architectural geometry. While the 15-amp motor and thin curved blade execute the cut, the engineering lies in the chassis rigidity. The cast aluminum base provides an absolute zero reference plane. The sliding rails, made of hardened linear bearings, allow for perfectly smooth, frictionless travel, while the miter and bevel scales use micro-detents to ensure absolute, repeatable accuracy to within fractions of a degree. The reciprocating saw, often termed the demolition solution, this tool maximizes linear kinetic force. The orbital motor converts high-speed rotation into powerful back-and-forth linear motion via a Scotch yoke mechanism. To prevent the tool from destroying itself, the massive internal counterweights are dynamically balanced, absorbing the colossal reciprocal inertia. It physically saws through timber, nails, and steel pipe with crude but highly engineered efficiency. The worm drive circular saw, the primary implement for heavy lumber frame construction. Conventional sidewinder saws maximize blade speed. This worm drive unit maximizes brute force torque. The motor is mounted parallel to the blade, utilizing a high-reduction worm gear transmission. This complex hypoid gear geometry provides a massive mechanical advantage, chemically converting motor speed into unyielding rotational power, allowing the saw to rip through wet, dense, pressure-treated timber without stalling. The angle grinder, engineered for high-velocity abrasive removal. To cut and grind metal effectively, high rotational speed must be maintained under varying load. The angle grinder's internal commutator motor spins at an incredibly high RPM. This rotational force is transferred through a simple bevel gear set, converting high-speed input into sustained high velocity at the output spindle. Crucially, the internal electronics provide closed-loop feedback, regulating torque to prevent the high angular momentum from stalling when pressure is applied to the abrasive disc. The electric hand planer, plenarizing rotational physics to create planar surfaces. Unlike a stationary planer, this hand tool utilizes localized high-speed shear force. The internal universal motor drives a heavy, precisely balanced cutter head featuring dual carbide blades. Spinning at excessive velocities, the blades exert massive rotational kinetic energy, physically shearing microseconds of material per cut. The resulting finish is determined not by the motor's power, but by the absolute rotational balance and cutting geometry. The random orbit sander, achieving finish clarity through dual-axis chaotic motion. A conventional rotational sander leaves distinct swirl patterns. This device breaks that symmetry. The main motor shaft drives an off-center counterweight which spins the sanding pad while simultaneously oscillating it side to side via an internal bearing assembly. This complex, randomized dual-axis movement creates a non-repeatable pattern, mathematically ensuring no single abrasive particle hits the exact same spot twice, completely eliminating scratch patterns. The plunge router, a high-speed milling machine utilizing for molecular-level wood separation. Routers require excessive rotational velocities to cleanly shear wood fibers without tear-out. This necessitates high-precision internal bearings that are dynamically balanced. The motor is engineered for continuous duty, converting immense quantities of electric potential energy into the centripetal and shear forces required to spin tungsten carbide bits cleanly through dense hardwoods. The concrete vibrator, utilizing eccentric rotation to achieve aggregate consolidation. To eliminate internal voids in a concrete pour, the tool must displace viscous fluid rapidly. Hidden inside the heavy steel vibrating poker head is a deliberately unbalanced eccentric internal mass. The flexible drive shaft spins this unbalanced weight at extremely high speeds. The resulting localized chaotic rotational energy violently radiates outwards, liquefying the viscous concrete mix and forcing trapped air bubbles to rapidly migrate and eject from the aggregate. The rotary laser level, achieving structural alignment via precision optical refraction. To generate an absolute horizontal reference plane, this tool relies on rotational consistency. The internal motor rotates a highly reflective prism assembly at precise, regulated intervals. When the high-power laser beam strikes the rotating prism, it refracts, projecting a continuous horizontal line across vast distances. The engineering challenge is maintaining the rotation frequency against internal friction and external vibration, ensuring the projected plane is perfectly flat and consistent over hundreds of feet. The forward plate compactor, harnessing chaotic inertia to achieve soil densification. While standard vibration cannot compact soil, localized chaotic kinetic impact can. The small gas engine or high-torque electric motor drives an eccentric weight system contained in the exciter housing. The speed of rotation is deliberately set to create resonant frequencies within the soil. As the heavy internal weight rotates chaotically, it generates immense downward kinetic energy spikes, which are physically hammered into the soil via the heavy steel plate, forcing the micromaterial particles into an immovable interlocked density. The core drill, high-torque rotational mechanics utilizing for precision material extraction. Normal high-speed drilling causes binding when drilling massive, deep holes in structural concrete. The core drill must manage excessive torque. It uses a robust, high-reduction planetary gearbox to convert standard motor speeds into massive rotational force at low RPMs. This enormous torque, combined with diamond-impregnated bits, provides the sustained cutting pressure needed to grind away structural aggregate while maintaining hole geometry, chemically converting immense quantities of power into raw turning force. The heavy demolition hammer, maximizing electropneumatic linear force for molecular separation. When standard impact tools fail, demolition requires maximum joules of kinetic force. Unlike a rotary hammer, this tool only generates linear percussion. A motor-driven piston compresses air, violently firing an internal striker into the chisel bit at thousands of impacts per minute. The internal mechanics rely not on rotary motion, but on absolute linear stability, utilizing heavy-duty counterweights and advanced dampening buffers to prevent the excessive reciprocal kinetic force from destroying the tool's primary chassis. The twin-cylinder air compressor, the centralized pneumatic generator. It does not apply force directly, it stores potential energy. An electric motor drives a dual-piston pump, violently drawing in ambient atmospheric air and compressing it into the reinforced steel tank. By forcing an immense volume of air into a heavily restricted space, it creates a massive reservoir of high-pressure kinetic potential ready to be instantly deployed. The pneumatic framing mailer, translating air pressure into immediate kinetic velocity. When the trigger is depressed, a highly calibrated valve opens, allowing the high-pressure air from the compressor to rush into the upper cylinder. This massive influx of pneumatic force violently drives a steel piston downward, striking the head of the fastener and embedding a 3-inch steel nail into dense lumber in a fraction of a millisecond. The powder-actuated fastener, utilizing controlled ballistics for structural anchoring. Pneumatics cannot pierce structural steel or cured concrete. This tool operates on the exact physics of a firearm. A specialized .22 caliber blank cartridge is loaded into the chamber. Upon firing, the chemical detonation creates rapidly expanding trapped gases. This microscopic explosion forcefully drives a hardened steel piston, sinking a concrete pin with unyielding ballistic force. The hydraulic bottle jack, utilizing Pascal's principle for massive force multiplication. This device relies on the fact that liquids cannot be compressed. By manually pumping the small outer cylinder, hydraulic oil is forced through a one-way check valve into the massive primary lifting cylinder. Because the pressure is distributed equally, the small input force is mathematically multiplied by the larger surface area, allowing a human hand to effortlessly lift 20 tons of structural steel. The airless paint sprayer, achieving surface coating via high-pressure hydraulic atomization. Traditional sprayers mix paint with blowing air, creating massive overspray. This unit relies purely on extreme hydraulic pressure. An internal pump pressurizes the viscous paint fluid to over 3,000 pounds per square inch. When this highly pressurized fluid is forced through a microscopic tungsten carbide orifice, it violently shatters into billions of perfectly uniform micro droplets, creating a flawless, glass-like finish. The gas-powered pressure washer, utilizing hydrokinetic shear force from molecular-level cleaning. The internal combustion engine drives an axial cam pump, accelerating standard garden hose water to devastating velocities. The water is forced out of the 0-degree nozzle at immense speed. This creates a concentrated hydrokinetic blade that physically shears dirt, oxidation, and loose material directly off the substrate surface without the use of chemical abrasives. The pneumatic rivet gun, executing blind mechanical compression. When accessing the rear side of a metal panel is impossible, this tool provides structural joining. High-pressure air operates an internal hydraulic piston, which violently pulls the mandrel of a blind rivet inward. This massive pulling force physically crushes and expands the aluminum body of the rivet against the rear of the metal panels, permanently locking them together before snapping off the access mandrel. The hydraulic knockout punch, shearing sheet metal via concentrated fluid pressure. Electricians must create perfectly round holes in thick steel electrical panels without working the metal. A pilot hole is drilled and a threaded draw stud is inserted. The manual hydraulic pump forces the sharp, hardened steel cutting die perfectly straight through the metal into the receiving cup. The localized hydraulic pressure applies flawless, even shear force, ensuring a surgically clean extraction. The manual PEX scrimper, a mechanical fulcrum engineered for hermetic sealing. Modern plumbing relies on cross-linked polyethylene tubing secured by copper rings. This manual tool is a pure force multiplier. The long steel handles and offset pivot points create extreme geometric leverage. When the handles are closed, the tool applies thousands of pounds of perfectly distributed radial compression, permanently crushing the copper ring into a flawless, watertight hermetic seal. The thermal imaging camera, visualizing invisible thermodynamic energy. To diagnose electrical faults or structural insulation failures, professionals cannot rely on the visible light spectrum. This device utilizes a microbolometer array to detect ambient infrared radiation. The internal processor chemically maps these microscopic temperature differentials, instantly generating a high-contrast visual gradient that exposes overheating wires or hidden moisture pockets. The digital multimeter, the electromagnetic diagnostic interface. Electrical systems present an invisible, lethal kinetic threat. This tool utilizes internal shunts and solid-state circuitry to safely interface with live circuits. By measuring the precise drop in voltage or mapping the flow of electrons, it converts raw electromagnetic potential into an exact numerical value, allowing electricians to trace microscopic continuity errors within massive architectural grids. The electronic stud finder, utilizing capacitive sensing for subsurface density detection. Finding structural timber behind drywall does not require destructive entry. This device emits a low-level electric field from its base. As the unit slides across the wall, it constantly measures the dielectric constant of the material beneath. When it passes over dense timber, the capacitance drops. The microchip registers this exact disruption, mathematically isolating the hidden structural mass. The pinned moisture meter, measuring molecular saturation via electrical resistance. Installing hardwood flooring over damp concrete guarantees catastrophic warping. This tool uses two sharp steel pins, driving them directly into the substrate. It passes a microscopic electrical current between the pins. Because pure water is a conductor, the internal computer measures the exact electrical resistance to precisely calculate the hidden molecular moisture content of the material. The laser distance measure, calculating architectural geometry via time-of-flight optics. Tape measures sag over long distances, corrupting the data. This optical tool emits a focused pulse of laser light directly at the target. The internal sensor measures the exact microsecond the phase-shifted light reflects and returns. Utilizing the constant speed of light, the processor calculates the spatial distance to an accuracy of 1/16 of an inch over hundreds of feet. The brass plumb bob, exploiting planetary mass to establish an absolute vertical vector. Before lasers, architectural verticality relied on pure gravitational physics. This dense, perfectly symmetrical brass weight is suspended by a string. Once kinetic swaying is dampened, the string aligns perfectly with the Earth's center of gravity. It is an unhackable, purely physical demonstration of gravity, generating an absolute, mathematically perfect vertical reference line. The chalk line reel, kinetic particulate transfer for planar alignment. To establish a perfectly straight layout line across a 50-foot concrete slab, builders use geometric tension. A high-tensile string saturated with fine chalk powder is pulled tightly across the surface. When the string is pulled upward and released, the stored kinetic energy causes it to violently snap against the concrete, transferring the chalk particulates to leave a flawless, unbending linear mark. The industrial heat gun, utilizing convective thermal dynamics to manipulate polymer structures. When bending PVC conduit or stripping layers of synthetic paint, open flames cause catastrophic carbonization. This device uses a powerful internal fan to force ambient air over superheated ceramic coils. It violently projects a highly focused stream of extreme convective thermal energy, safely raising the target material precisely to its localized melting point. The precision soldering iron, creating molecular bonds via localized conductive heat transfer. To permanently join copper pipes or delicate circuitry, mechanical pressure is insufficient. This tool converts electrical energy into intense localized heat at the copper tip. When applied to the joint, it transfers this thermal energy via direct conduction, raising the temperature until the separate metallic alloy violently melts, capillary action drawing it in to form a flawless permanent molecular bond. The mechanical pipe bender, leverage geometric deformation of steel pipe. Forcing a steel pipe to curve 90 degrees without collapsing the internal wall requires extreme mechanical discipline. This heavy steel fulcrum features a highly calibrated grooved die. As the long handle is pulled, it exerts massive leverage, physically stretching the outer wall of the steel pipe, while the unyielding internal die prevents the structural geometry from buckling inward. The click-type torque wrench, applying exact calibrated mechanical tension to structural fasteners. In high-stakes engineering, over-tightening a bolt causes the steel to microscopically fracture. This precision instrument features a calibrated internal spring and cam mechanism. The user dials in the exact foot-pounds required. When that exact kinetic threshold is reached, the cam physically slips, producing a tactile and audible shockwave to prevent catastrophic overtensioning. The automatic rebar tire, automated kinetic spooling for structural steel binding. Manually tying thousands of steel rebar intersections with pliers is a massive drain on localized kinetic energy. This battery-operated tool completely automates the physics of wire binding. Upon triggering, internal gears violently spool, wrap, and twist a high-tensile wire perfectly around the steel joint in under 1 second, mathematically ensuring identical, unyielding tension across the entire foundation grid. The precision wire stripper, exact radial shear for insulation removal. Stripping electrical wire with a standard blade frequently scores the underlying copper, creating dangerous microfractures in the conductive lattice. This tool utilizes perfectly sized, geometrically opposed cutting Ds. When closed, it physically shears the external polymer insulation exactly down to the microscopic surface of the copper wire, allowing the casing to be pulled away without damaging a single strand of the delicate metal inside. The optical theodolite, establishing planar geometry of the optical triangulation. Laying out a massive skyscraper foundation requires absolute horizontal and vertical perfection. This precision optical instrument utilizes internal pendulums, highly polished lenses, and micro-calibrated rotational axes. It completely isolates the operator's eye, allowing them to measure exact geometric angles between distant points with microscopic accuracy, converting raw topography into a flawless mathematical grid. The ground-penetrating radar scanner, utilizing electromagnetic pulse reflection for subsurface mapping. Before drilling into structural concrete, engineers must locate hidden post-tension cables. This heavy unit slides across the concrete, firing massive bursts of high-frequency electromagnetic pulses deep into the solid mass. The internal processor measures the exact reflection signatures bouncing off hidden steel or conduit, generating a flawless real-time 3D subsurface map without breaking a single piece of concrete.